Hello ladies and gentlemen, Unit 2 Study Guide. We got the crash course, we got the study guide, you got the quiz review on Schoology. If you can do all this stuff, you're going to do just fine. So let's go through this, and I'm going to kind of skip some of this stuff because we didn't get to it this year. COVID's annoying. So first thing, increasing intervals. So when we talk about increasing intervals, we're talking about where, as I read left to right, the function is going up. So if you look, you're like, oh, well, here it's going up, and here it's going up. Now, the thing about intervals is, when you are describing intervals, you are only going to list x values. So remember, we're talking about as you go to the left and to the right. So as you go to the left, x is going to negative infinity, and then it is increasing until you get to this x value, which is negative 2.528. That's the first interval of increasing, and I think we've said we're going to use brackets for all of these endpoints except for infinity. Then union. This is not an interval of increasing. This is those, so we'll say starting at 0.528 and going on forever as x goes forever and ever to the right, we are continuing to be increasing. Decreasing intervals is going to be when you go down as you read left to right, so that would be negative 2.528 to 0.528. Remember, these are only x values. A local minimum is a minimum on an interval, so local minimum is a turnaround point like down here. That's a minimum, so we'd say 0.528 and negative 1.128. That's an ordered pair, so it's in parentheses. Local maximum, right here, negative 2.528 and 13.128, also an ordered pair, so it should be in parentheses. And then boundedness, so if this thing has a maximum or a minimum, like a global maximum, throughout the whole function. This thing doesn't. It goes up and down forever. So since the range is going to be negative infinity to positive infinity, this is unbounded. It's not bounded above. It's not bounded below. We can say it's unbounded. All right, let's use a table to evaluate some functions. So if I say what is f of 2, that means I want you to plug 2 in for x. Well, here's the x values. So let's plug 2 in for x, and you get 0. Okay? G of 3, so find the x value 3 right here. G would be negative 3. G of f of 4. First, let's find f of 4. F of 4 is 3, so then what I really want is g of 3. G of 3, I just found that. It's negative 3. So g of f of 4 is the same as g of 3 because f of 4 is 3. Now it says find a function composition so that the output is negative 2. So where's negative 2? Right here. How can I get negative 2? Well, that's g of 2. So g of 2 will give you negative 2. So then how can I get a 2? Well, if I wanted to get a 2, I could say f of 0. So if I do g of f of 0, I think that should be negative 2. So let's kind of look at it. F of 0. So if I find the inside first, f of 0 is 2. Right there, good. Now I want to find g of 2. G of 2 is negative 2. So there's your function composition. That means you plug a function into another function and you get an output that is negative 2. That's kind of tricky. Odd even functions didn't make the cut 2020. Sorry, odd even functions. We didn't do odd even, but we can talk about boundedness. So this is what I said before. This thing goes up and down forever, which means this is not bounded. So we'll just say it's unbounded, or let's say unbounded. That's probably the best word. Unbounded. It goes up and down forever. This one, though, does have a maximum. So there's a y value that I never go above. It looks like it's probably 1 or so. There's a y value that this function never goes above. So this function is said to be bounded above. There is a maximum to it. So it's bounded above. There's a boundary above the function, if that helps you. Domain of f of x. Okay, so we're going to find some composite functions and find some domains here. So domain of f of x, you look at f of x, that's right here. You're like, well, the denominator can't be 0. So if you factor the denominator, you get x plus 3, x minus 3, which means x cannot be negative 3 and x cannot be positive 3. Everything else is fine. The denominator just can't be 0. So in interval notation, that's negative infinity to negative 3. Pick up your pencil. Negative 3 to positive 3, pick up your pencil. And then 3 to infinity. That's not the best infinity sign. Let's make it better. That's all right. Okay. Now let's do domain of g of x. So g of x is a radical, which means x plus 8 has to be non-negative, which means x has to be greater than or equal to negative 8. That would be negative 8 to infinity, and that would be a bracket because it's a closed circle. You can plug in negative 8. You can take the square root of 0. So identify any discontinuities for f of x and their x value. Okay, discontinuities. The discontinuities are at -3 and +3, and they are both going to be infinite discontinuities. So there are infinite discontinuities. That means that they didn't get removed. They're going to be vertical asymptotes. Discontinuities at x equals -3 and x equals +3. Infinite discontinuities are vertical asymptotes. Since the factor, actually this one, I'm sorry, I didn't even look at the question. That's wrong. One of these is going to be removable. There's an infinite discontinuity at -3, but this cancels out actually. So that means there is a removable discontinuity at x equals +3. So since this factor cancels out, that's actually a removable discontinuity. So there's an infinite discontinuity at -3, and there's a removable discontinuity at x equals 3. So what I'm going to do is we're going to graph this thing, and let's see, where's my Desmos? It was x minus 3 over x squared minus 9. And we're going to find the two discontinuities. One of them is going to show up as an asymptote. That's the easy one. See, -3, you can tell there's a vertical asymptote. So that's your infinite discontinuity. But there's also a removable discontinuity at x equals 3. That one you probably won't see unless you go right to, oh, there it is. See, there's a hole in the graph at 3. So when you draw it, you got to make sure you put a hole in the graph. So vertical asymptote is an infinite discontinuity at -3, and at +3, we have that removable discontinuity. That's the hole in the graph. And the reason that happens is because when you factored, one of these cancels out. All right, now let's do g of h of x. So g of h of x means you're going to plug h into g. So we're going to take this function, and instead of writing x, we're going to take h of x and write it. So it'll be the square root of, instead of x, x squared minus 9, and then it's plus 8. So this is the square root of x squared minus 1. That's the composite function g of h of x. Domain of g of h of x. So this is where it's kind of tricky. And this is a nonlinear inequality, so it's especially tricky. The domain of g of h of x. First, look at the domain of the input function. That's h of x. And you'll notice h of x is a parabola. It doesn't have any domain restrictions, so there are no domain restrictions for that. But then you look at the function that you create and see if there are any domain restrictions. And the answer is yes, there are going to be, because x squared minus 1 has to be greater than or equal to 0. Now, the best thing to do, I think, is to sketch the graph of x squared minus 1. I know that there are zeros at -1 and 1, and if you want, you can even find the y-intercept. So if this is the graph x squared minus 1, and I need it to be positive, where does that happen? That happens to the left of -1 and to the right of 1. So the domain of the composite function is the domain of this. That's -infinity to -1 with a bracket, union, 1 to infinity. The radicand has to be positive. So graph the radicand and tell me where it's above the x-axis. It's above the x-axis to the left of -1 and to the right of +1. So using interval notation, that's how we describe the domain. Okay. Continuous or not? So we've got a couple more problems here. Let's see, is this continuous? Well, it's got a denominator x squared minus 4, so it's not going to be continuous. This is x plus 1 over, if you factor the denominator, x plus 2, x minus 2. So, like I was saying in the other problem, since neither of the factors cancel out, that means there are going to be two infinite discontinuities. And they are going to be at x equals -2 and x equals +2. Now, I'm going to just use Desmos to keep this thing moving. X plus 1 over x squared minus 4, x plus 1 over x squared minus 4, and I should see, the main thing is that I can see there are two vertical asymptotes, and the two vertical asymptotes are at +2 right there and -2 right there. So those are my infinite discontinuities, and those are because the denominator can't be 0. Let's try another one. So I'm going to have to factor the numerator. I know there's a discontinuity at 2, but I'm not sure what kind. So to figure that out, I'm going to factor the denominator. So let's see, what multiplies to 20 and adds to -12? I think if I do -10 and -2, that'll do it. So then I do grouping, 5x, x minus 2, minus 2, x minus 2. So my factors are 5x minus 2, and x minus 2. And wouldn't you know it, since the denominator is x minus 2, this factor cancels out, which means I have a removable discontinuity. My handwriting is rough on this thing. At x equals 2. It's rough anyway. At x equals 2. So that means there's a hole in the graph. Now, this is just a line. If you look at y equals 5x minus 2, you'd start at negative 2 and go up 5 over 1, up 5 over 1. 5x minus 2 is just a line with slope 5. But what's going to happen here is at x equals 2, that's right here, that's going to be an open circle. So you need to make sure that it's very obvious in your graph you have an open circle at x equals 2. Let's graph it in Desmos 2. 5x squared minus 12x plus 4. 5x squared minus 12x plus over x minus 2. And, wait a minute, hold on. I copied. I'm missing an x. 12x. There we go. All right, so you can see I've got my line starts at negative 2, the y-intercept, and it goes up 5 over 1 right there. So there's that other point I drew. But then at 2, x equals 2 right here, maybe? Yep, right there. There's your hole in the graph. Your removable discontinuity. And that happens because the factors canceled out. Okay. What else you got? Difference quotient. All right, so the difference quotient, we're just going to plug in a plus h everywhere I see an x. And then, so that's instead of x squared, that's a plus h squared. We'll subtract f of a, so I'll plug in a everywhere I see an x. Okay, now the main thing is you remember that a plus h squared is a squared plus 2ah plus h squared. You need to FOIL that out. Minus 2, and I'll go ahead and distribute here. All over h. The two biggest things people make mistakes on is they don't FOIL this correctly and they forget to distribute the negative. So minus 3a squared plus 2. So let's go ahead and distribute 3a squared plus 6ah plus 3h squared minus 2 minus 3a squared plus 2 all over h. What goes away? Hopefully some stuff. 3a squared, negative 2, positive 2. Yep. So I have 6ah plus 3h squared over h, and then I will factor out an h because I want to be very careful. 6a plus 3h over h. So my difference quotient is 6a plus 3h. Okay, 6a plus 3h. Let's do another one, and then we'll be done. So difference quotient, a plus h squared minus 3a plus h plus 4. There's f of a plus h minus f of a squared minus 3a plus 4, all over 4, or I'm sorry, over h, rather, h. FOIL, a squared plus 2ah plus h squared, and distribute, minus 3 minus 3h plus 4 minus a squared plus 3a minus 4, all over h. So this is just a bunch of distributing. A squared, negative 4, positive 4, 3a. Okay. 2ah plus h squared minus 3h, all over h. Now I will factor out an h. 2a plus h minus 3 over h. So my difference quotient is 2a plus h minus 3. Okay, difference quotient done. What else you got? That might be it. I think that's it. Is there something else in there I'm missing? I feel like there might be, but it's not something we're going to cover. Yeah, we're good. All right, cool. That's it. We're done. So if you can do all that, you can ace this test. So good luck. Make sure you get all your work done, and like and subscribe.